Okay, so for homework yesterday, you guys were given the function f of x is equal to e to the x times cosine x, and they gave you a domain 0 to 2 pi. Notice they use brackets here, so that means 0 and 2 pi are included in our domain. And then they asked you to find x coordinate of any inflection points. Okay, so as we should know, the steps for finding inflection points are to take the second derivative, I don't know how to spell. The second step is to set to 0, and we're just going to add the next step to solve. And then usually I think this is the fourth step, but I'm trying to save time. We're going to check those points on our horizontal line test. So that being the case, step one, let's take the second derivative. So to get the second derivative, we're going to have to take the first derivative first. And we notice we have a product of two functions here. So our first function is e to the x, our second function is cosine. So the first times the derivative of the second, the derivative of cosine is negative, don't forget that negative, sine, plus the derivative of the first times the second. The derivative of e to the x is still just e to the x. So there we go, there's the first derivative. And if you need that reminder, you can, just put the domain back on your derivative as well, so you don't forget about it. Second derivative. So here we have another product. So we're going to have the derivative, or leave the first, times the derivative of the second. And let's use brackets just so that we keep ourselves organized. So that is the first times the derivative of the second plus, but there's a negative there, so we're just going to switch that to a minus. So plus the derivative of the first times the second. So that is all the derivative of our first term. And then plus, and e to the x cosine x is exactly what we took the derivative of in the first, when we took the first derivative. So I'm just going to copy down our f prime here. Negative e to the x sine x plus e to the x cosine x, and close our brackets out. Perfect. So now we should see that we've got our second derivative completed, but it's not the prettiest. And it seems that everything's e and sine. So let's just pay attention to see if we can cancel things out. Here we have a negative e to the x cosine x. So then my other cosine term is over here, e to the x cosine x. However, this one is positive. So that means this is going to cancel with that. And then here we have a negative e to the x sine and negative e to the x sine. It's the same thing. So those are going to combine. So we have f double prime is equal to negative 2 e to the x. That should have been a sine. 2 e to the x sine x. Perfect. So first step done. We took the second derivative. Now we need to set that equal to 0 and solve. So negative 2 e to the x sine x. You could divide both sides by negative 2 e to the x, and then you'd get sine x equals 0, and you can solve it there. Or you can look at this and say, well, e to the x will never be 0. Therefore, this function is only 0 when this is 0, when sine x is 0. So either way, you're going to get 0 equals sine x. And so now, what x values, and remember our domain is from 0 to 2 pi inclusive, so 0 and 2 pi are included. So what values within the unit circle make sine 0? Well, sine is 0 when x is 0 and when x is pi. Let me just imagine the unit circle real quick, make sure that's right. Yep, sine is 1 at the top and the bottom. So the right and left, sine is 0, 0, pi. And remember, 2 pi is included in our domain as well. So we need to include that. Even though 0 and 2 pi are the same value on a circle, the sine graph is going to look something like this, right? So 0 and 2 pi are actually two different values when you graph it out. But when you just have a circle, 0 and 2 pi are both right there. Okay, so be careful. We need to include all three. And then we just have to test those out on our horizontal line test. And because they gave us a closed domain, we do not use arrows on our line test. We just close it off here. And 0, 2 pi, and we're just missing pi, which goes right in the middle. And so now we need to plug in values and see whether they are positive or negative. So I would suggest using pi over 2 and 3 pi over 2. Those are easy values. And you can plug those values back in to our original, well, to our second derivative. Okay. If you plugged those values in here or here, in this case, it's not going to matter because this one doesn't matter. This one, however, it looks like you're going to be wrong if you plug in there because we got rid of that negative sign. So let's make sure that we are using our second derivative before we manipulated it, before we did algebra to solve for x, okay? Because as you can see, or as you will see, that can change the value. So if we put pi over 2, notice e to the x will always be positive. No matter what you put into x, e to the x is positive, so there's no need to check that. Sine of pi over 2 is 1, and 1 times negative 2 is going to give us a negative here. If we would have put that here, we would have got positive, and so we would have been wrong. For this problem, they only care about the inflection points, so it wouldn't have mattered too much. But if they asked you to find where it's concave up and concave down, you would have been flipped. And this one's going to be positive. If you put it in, sine of 3 pi over 2 is negative 1, and then negative 2 times negative 1 gives us a positive. So pi is our inflection point. And you might ask, why not 0 and 2 pi? And that would be a great question. Give me 1 second. More. And the answer to that question is that because at the end point, it's impossible for the concavity to switch from concave up to concave down. So what I mean by that is, here's pi. As you notice, to the left of that, we have a graph or a function that's facing down, and to the right, it's facing up, right? So it switches from down to up. Whereas at the end points, it ends. So it's not possible for it to switch if there's nothing to the left or to the right of that point. Okay, if it's the start point or the end point, there's nothing for it to switch. Similar to how endpoints cannot be relative mins and maxes. That's because to be a relative min and max, you have to be bigger or smaller. You have to have a value bigger or smaller than the points to the left and to the right of you. But if those points don't exist, well then you can't be a relative min or max. You can't be an inflection point. So pi is our only inflection point. The problem that I want to do today involves something called Riemann sums. So before I do the problem, let's just draw some kind of a graph. And let's do it like this so that math is easy. 10, 10. If I told you, let's say this is f of x, if I told you to find the integral from 0 to 10 of f of x, don't worry about this dx there. It's just something that you have for integrals. There's a reason for it, but the reason's not important, so don't worry about it. You should know, based on the problem I did yesterday, that an integral is the area under a graph, or the area between a graph and the x-axis. And you notice that this just makes a nice, neat triangle. And so our answer would be 1/2 base times height, which is 50. I didn't give you any units here, so your answer would just be 50 or 50 units. And that's all fine and dandy. Sometimes, go back, there we go. Sometimes you do not have such a nice, fine, and dandy graph. And so you are not able to just make up shapes, and then you know the area formula for those shapes, and you just add up the area, and you can get it like that. Sometimes a graph is curvy in such a way that you can't, it doesn't make a shape that you would know the area of. So for problems like that, or problems where they give you just a table of values, and so maybe you don't know what's happening in between. All you know is that here's x and here's y. It goes from 1 to 2 to 3, and it goes from 0 to 6 to 15, I don't know. And so all you would have on your graph are some points. 1, 2, 3, goes here, and 2 goes up to 6, and 3 goes up to 15. All you have are these points. You don't know what's happening in between. In order to find the integral, which is a really important thing that we need just in general, it tells us in real life some important things, but we'll go over that later. In order to approximate the integral, we need a way to do that, even if we can't just use shapes. So what we use is something called a Riemann sum. Okay. A Riemann sum means let's just take some rectangles, the closest rectangle that we can to what we have, and we'll use that. We'll find the area of those rectangles, and we'll say, that's close enough. I mean, sure, we're off by that much, and sure, we're off by that much, but we're going to get way closer than if we just make something up. So this is what a Riemann sum is. Let's give us tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are, wow, those are pretty nicely spaced. I'm pretty proud of myself. There are different types of Riemann sums. You might hear something called a left sum or a right sum, and it's not confusing at all. All it means is take your x spacing, so in this case we're spaced by 1, and if we are going to do a right Riemann sum, you start from the right end of that space. So notice the right end gives us, we're at 1, so we go up to our function value, and then we just draw a rectangle based on that left value. So it would look like this. So this is what the process would be if I said use a left Riemann approximation, or a left Riemann sum approximation. You would do something like this. And then you just have to find the area of each of these values. So you should know that it's, this is a function of y equals x. So at 1, the value is 1, and the area of a rectangle is length times width. So the area of this rectangle is 1. The area of this rectangle is 2 times 2, which is 4, and 9, and 16, and so on and so forth. It would go up, and you would add all those up, and you would get the same answer as if you just, you would not get the same answer as if you just took the derivative normally, because you have all these extra triangles that are off. Similarly, we could use the process of a left Riemann sum. So here we have our interval. And so here we would, instead of using the right value, we would use the left value. So because our left value is at 0, there's no rectangle there. But then we have one here, and then we go up to here, right? Our values here. Oh, sorry, left here. Left is here. Left is here. So on and so forth. And as you can see, for this particular graph, a right Riemann sum is going to give us something too big, and a left Riemann sum is going to give us something too small. You could also use what's called a middle Riemann sum. And take a guess, instead of starting on the left or the right, you start drawing your rectangle from the center of your interval. So we're going to come here, and then we'll come here, and then we'll come here, so on and so forth. And as you can see, for this particular graph, a middle Riemann sum is actually going to give us, I think anyways, it's going to give us the right answer, because for every little bit that we have over here, too much, we have another little bit here, which is not enough. And so those cancel out, I think anyways. Perfect. So that gives you an idea of what a left and right Riemann sum is. The problem that I want to do tells us, or asks us rather, to approximate the integral based on a table of values. So they say 0, 0, 2, 4, 5, 13, 7, 21, and 8, 23. By the way, I just realized that when I was doing my my right sum or my left sum, whatever, I was taking the area. Let's say this is a 3 and this is a 2, and so this is a 3. I said the area of that rectangle would be 9. That's way off. The width of this rectangle is only 1, and 1 times 3 would only be 3. So actually, each of my triangles would only be like that. It would be 1, 2, 3, so on and so forth, and it would go up from there. It would not be 1, 4, 9. That's crazy. I don't know how to do math. Okay, so I just wanted to correct myself on that one, in case you guys didn't catch me on that already. So here's our value, and this one they ask us to use a trapezoidal sum. Okay, so similar to a left or a right Riemann sum or a mid Riemann sum, a trapezoidal sum means we just take trapezoids. So our x values are at the top, and technically they say this is a t and an e. So here we have e and t, and the first one is a 4. The next one is a 13. Sorry. The first one is not a 4. The first one is a 0, and then a 2, and then a 5, and then a 7, and then an 8. And then the y values for those points are going to be 4, 13, 21, and 23. So we have a point here, we have a point here, we have a point here, and we have a point there. So what we're going to do here is make trapezoids. So we start with where we're at, and we have that, and then that, and that, one more, like that. So here we have 4 trapezoids. For a trapezoidal sum, instead of making rectangles where you go just up and down straight across, for the trapezoidal sum, you go straight to the next value. And so then you take the area of each of these shapes, and you would get your final answer. In this case, let's see what they have. They told us to do 18 times 0 to 8 of e of t. And so this would be 4. This one's going to be 3 times halfway in between 4 and 13. If you go up 5, you get 9 from 4. If you go down 5 from 13, you get 8. So this is going to be 8.5 times 3, which is 25.5. And then this one is going to be, our spacing here is 2 times the average value. If you go up 5 from 13, you get 18. So go up 4, you get 17. And then you go down 4, you get 17. So this is 17. So this is going to be 2 times 17 is 34. And then this one is, the average value here is 22. And it'll be 22 times 1 is just 22. So then you would add all those up and you would get your answer. So this has been a lesson on how to do Riemann sums. For those of you who've been looking for videos on the stuff we've not yet hit in class. And then here's your answer for your homework. Hope you guys are doing well. I'll see you next time.